Late Permian, about 252 million years ago, the world is one unbroken horizon. The supercontinent of Pangea dominates the globe, stretching almost from pole to pole. It is a continuous landmass of staggering scale. The rest of the planet is covered by a single global ocean called Pangea. Weather systems born over this massive sea batter the coastlines with incredible force. Yet, they exhaust themselves before reaching the deep interior. The heart of Pangea is an endless, punishing desert. This is a harsh, extreme world. But life endures. Ancient lineages of amphibians and reptiles populate the coastal swamps and river valleys, deep beneath their feet. However, the architecture of the planet is shifting. The crust is a fragile skin. The heat of the solid mantle below is beginning to rise. Present-day, geochronology lab. It sits on a glass slide, barely wider than a human hair. It is a microscopic grain of zircon. In this quiet, sterile room, a technician carefully loads a tray of crushed basalt into a mass spectrometer. The machine hums to life. Its purpose is to count individual atoms trapped inside a crystalline lattice. We extract these specific crystals from rock samples taken from the Siberian Traps. The physical process of isolating them is slow and exact. Zircon is incredibly resilient, surviving extreme heat and immense pressure without melting or breaking down. When it originally forms in cooling magma, its structure accepts atoms of uranium. It completely rejects atoms of lead. This chemical quirk is vital, because uranium is radioactive. It decays into lead at a known constant rate. Every atom of lead found inside a zircon crystal today was born from uranium decay. The rock acts as a stopwatch. By counting the ratio of uranium to lead inside the vacuum chamber of the spectrometer, we calculate when the lava cooled and solidified. This method provides an absolute date, tying ancient rock directly to our modern calendar. Burgess et al. 2014, Late Permian, about 252 million years ago, the mantle breaches the surface. In the region we now call Siberia, the crust simply gives way. This is not a single mountain erupting with ash and fire. It is a vast network of fissures tearing the ground open across roughly 2 million square kilometers. Lava floods the landscape in relentless, heavy waves. The eruptions do not stop. They continue for hundreds of thousands of years, burying the earth in deep layers of basalt. But the lava itself is not the true killer. The real danger is invisible. As the magma rises, it burns through thick underground deposits of coal and carbonate rock. Trillions of tons of carbon dioxide and sulfur are vaporized and blasted into the atmosphere. The sky darkens with a toxic, heavy haze. Global temperatures spike dramatically over a geological instant. The oceans absorb the immense volume of carbon and become violently acidic, slowly dissolving the shells of marine organisms. The water warms, losing its ability to hold oxygen. The marine ecosystems collapse completely. The timing is not a coincidence. Present-day, data analysis. We look at the dates extracted from the zircon crystals. The numbers are precise. The peak of the Siberian magmatism aligns closely with the greatest die-off in the fossil record. They are simultaneous events. The mass spectrometer locks the age of these basalts to exactly 251.9 million years ago. At this specific stratigraphic horizon, 90% of all marine species disappear from the rock record. 70% of terrestrial vertebrate species vanish alongside them. The evidence points to a suffocated world. Burgess et al. 2014. We can't tell the exact daily weather of Pangea from this evidence. What it does support is the precise overlap of the volcanic eruption and the extinction. The dating is absolute. The rock preserves a record of global atmospheric collapse driven by deep earth tectonics. This was a near-total sterilization of the biosphere. Early Triassic, about 250 million years ago, the world is eerily empty. The massive forests that once covered the humid zones of Pangea are gone, replaced by simple ferns and resilient fungi. The soils, stripped of their deep roots, wash away into the choked, muddy rivers. Without the great herbivores to anchor the food web, the large predators have starved. Only a few hardy lineages remain in the ash. One of the most successful is a strange, stout animal called Lystrosaurus. Reconstruction based on fossil distribution shows this pig-sized herbivore dominating the barren, baked floodplains. It is not particularly fast. It is not particularly intelligent. But it can dig for roots. And it can survive in air with lowered oxygen levels. In the wake of the apocalypse, Lystrosaurus thrives simply because the competition is dead. It inherits an empty earth, but Lystrosaurus is not alone. In the shadows of this devastated landscape, another group of survivors is beginning to quietly diversify. These are the early archosaurs. They are small, lightly built reptiles. Reconstruction constrained by early biomechanical models suggests some are experimenting with a more upright posture, pulling their legs directly beneath their bodies. This structural shift allows them to move with greater efficiency, saving precious energy in a starved, unforgiving environment. They can breathe while they run. This is a biological revolution. Over millions of years, these early archosaurs will radiate into the empty ecological niches left behind by the extinction. They will become the dominant terrestrial predators. They will eventually evolve into the massive, long-necked herbivores that will define the coming eras. They are the ancestors of the dinosaurs. Their evolutionary reign will be shaped entirely by the shifting ground beneath them. Because Pangea is not a stable home, the mantle convection currents that fueled the Siberian Traps are still churning deep underground. The heat has not dissipated. It is merely seeking a new weakness in the crust. The supercontinent is a temporary arrangement. Its time is rapidly running out. Late Triassic, about 200 million years ago, the deep heat finds a flaw. Beneath the dry heart of Pangea, massive upwellings of hot mantle rock push against the solid lithosphere. The supercontinent is stretched thin. Immense pressure builds, bowing the land upward until the tension becomes unbearable. And then, the crust cracks. A long, jagged fracture opens between what will eventually become North America and Africa. It is a slow, relentless tearing. It expands only a few centimeters a year. But over geological time, centimeters add up to continents. A deep rift valley forms, sinking as the land on either side pulls away. Present-day, field site, the geologist holds the water-cooled diamond drill steady against the dark rock face. Water splashes over the spinning bit as it bites into the exposed basalt. It cuts a clean, perfect cylinder, barely the size of a roll of coins. Before snapping the core free, the geologist carefully marks its orientation relative to the modern sun. This captures a physical compass. When lava erupts and begins to cool, tiny crystals of magnetite inside the molten rock align themselves with the Earth's magnetic field. They act like microscopic compass needles. They point toward magnetic north. Once the rock solidifies, that orientation is locked in place forever. By analyzing these tiny magnetic signatures in the lab, we can determine the approximate latitude where the lava originally cooled. We can track how the rock moved. The evidence points to continents in motion. Present-day, data analysis. We plot the magnetic data on a map of the ocean floor. The pattern is unmistakable. The Earth's magnetic field occasionally flips. Magnetic north becomes magnetic south. And vice versa. As new lava erupts along the mid-ocean ridges and cools, it records these flips as a series of alternating stripes on the sea floor. It creates a massive barcode. This maps oceanic crust spreading outward symmetrically from the central ridge. This magnetic striping demonstrates that the Atlantic Ocean is expanding. The Americas and Africa are pushed apart at roughly the speed fingernails grow. Seafloor isochrons indicate the central Atlantic began opening during the late Triassic and early Jurassic. The ocean crust in the middle of the Atlantic is entirely new rock. It was generated millions of years after the continents themselves formed. The land masses didn't just slide through an existing sea. They created a new ocean between them. Seaton et al. 2012. We can't tell the exact day the crust snapped from this evidence. What it does support is the steady, measurable rate of seafloor spreading. The magnetic barcode provides an absolute timeline for the physical division of the planet. It tracks a torn world, early Jurassic, about 180 million years ago. The Rift Valley deepens. It finally drops below sea level. Salt water from the global ocean floods into the massive trench. A shallow, narrow sea now divides the landmass. Pangea is broken into two massive supercontinents, Laurasia to the north, and Gondwana to the south. The single, unified landscape is gone. Reconstruction shows the edges of this new sea lined with early dinosaurs. Navigating a world that is fundamentally changing. Rivers that once flowed inward toward the deserts now reverse course. They drain into the new Atlantic. The climate begins to shift as the vast inland deserts are suddenly exposed to coastal moisture. The environment is fracturing along with the crust, for the animals living on the margins of the rift. The widening sea is an absolute barrier. Herds that once migrated freely across the equator are now permanently divided. The genetic exchange is severed. The isolation begins. A species split across a newly formed ocean will face slightly different environmental pressures on either side. Over tens of millions of years, the slow accumulation of mutations and adaptations will drive them apart. One species becomes two. The physical rupture of the Earth is the engine of biological diversity, forcing evolution down divergent paths. The continents have become enormous. Drifting life rafts. Early Cretaceous, about 130 million years ago, the southern supercontinent of Gondwana begins to fracture. The same mantle forces that opened the central Atlantic now tear south, driving a wedge between South America and Africa. The rift snakes downward. It follows the path of least resistance through the ancient crust. It is a slow, methodical separation. For millions of years, the two massive land masses cling together along a narrowing land bridge. A final connection before the Southern Ocean completely breaks through. Present-day, museum collections. The metal drawer slides open smoothly, revealing a row of small, delicate fossils resting on archival foam. They belong to Mesosaurus. This was an early aquatic reptile with a long, thin snout lined with needle-like teeth. A paleontologist carefully lifts a specimen labeled with a collection tag from southern Brazil. Beside it, she places an almost identical fossil extracted from the Karoo Basin in South Africa. The bones are indistinguishable. The anatomy is a perfect match. This simple comparison is a cornerstone of our understanding of the deep past. Mesosaurus was a coastal animal. It was adapted to shallow, brackish waters. It was completely incapable of crossing thousands of miles of deep, turbulent ocean. Yet, its remains are found locked in similar layers of Permian rock on continents now separated by the vast expanse of the South Atlantic. This fossil distribution indicates that these specific regions of Brazil and South Africa were once physically connected, sharing the same freshwater lakes and coastal swamps. The animals didn't cross an ocean, the land beneath them simply moved apart. Present-day, biogeography context, we map the distribution of early terrestrial fossils, ferns, heavily armored reptiles, and primitive amphibians, across the southern continents. The patterns align closely across modern coastlines, acting as biological puzzle pieces that fit the geological boundaries. But as the early Cretaceous progresses, the shared fossil record abruptly ends. The lineages found in the rock layers above the split begin to look completely different. We can't tell the specific breeding behaviors of these animals from this evidence. What it does support is that the newly formed deep ocean became an impassable geographic barrier. The genetic isolation was absolute. South America was effectively severed from the rest of the world. It began a journey as a massive island continent. Late Cretaceous, about 90 million years ago, South America drifts westward in total isolation. The separation acts as a profound evolutionary pressure cooker. without competition or genetic input from other landmasses. The animals trapped on this drifting raft begin to radiate into bizarre, highly specialized forms. Reconstruction shows the dense, tropical environments of the South American island teeming with unique lineages. In the shadows of massive sauropods, early mammals diversify rapidly, lacking the placental predators that dominate the northern continents. A strange array of marsupials claim the ecological niches of large carnivores and specialized herbivores. Massive, flightless terror birds eventually evolve. They rule the open plains as apex predators. The isolation fuels an explosion of biodiversity that looks like nothing else on the planet. Meanwhile, on the African side of the rift, evolution takes a different path, driven by a different set of climatic and geographical pressures. The biological divergence is entirely the product of plate tectonics. The mantle convection that ripped the continents apart dictated which animals survived, which went extinct, and which mutated into entirely new forms. The physical map of the world is not just a stage for evolution, it is the active architect shaping the biology of every living thing. The hothouse world of the Cretaceous is highly fragmented. This sets the scene for an external shock that will test the resilience of every isolated ecosystem. Eocene, about 50 million years ago, Antarctica is not a wasteland of ice. It is a forested continent, connected to the southern tip of South America by a narrow land bridge. The climate is cool but temperate. Reconstruction shows dense stands of early beech trees and conifers covering the coastal regions. These forests support a diverse array of early mammals and birds. The surrounding oceans are warm enough to sustain complex marine ecosystems. But the tectonic drift that ripped Pangea apart has not stopped. The Australian plate has already broken away and is migrating north. Now, the final connection between South America and Antarctica begins to pull apart. It stretches thin, Eocene-Oligocene boundary, about 34 million years ago. The land bridge snaps. The ocean breaches the gap, fully severing the two continents. This new, deep water channel is the Drake Passage. Its opening fundamentally rewrites the global climate. With Antarctica now isolated by open ocean, nothing stops the flow of water circulating around it. Driven by relentless westerly winds, a massive, unbroken current establishes itself. The Antarctic circumpolar current begins to roar around the continent in a continuous loop. It acts as a massive thermal wall. It prevents warm, tropical currents from the north from reaching the Antarctic coast. Cut off from the global heat exchange, Antarctica rapidly cools, present-day, core repository, in a massive, climate-controlled warehouse. Long plastic tubes hold cylinders of mud extracted from the deep ocean floor. A technician carefully slices a core open, revealing layers of gray sediment. These layers are packed with the microscopic, calcium carbonate shells of benthic foraminifera. These single-celled organisms lived on the ancient sea floor. When they build their shells, they pull oxygen atoms directly from the sea water. By running these shells through a mass spectrometer, we measure the ratio of two oxygen isotopes, oxygen-16 and oxygen-18. Oxygen-16 is lighter and evaporates more easily. When global temperatures drop and massive ice sheets form on land, that lighter oxygen-16 gets trapped in the glacial ice. This leaves the oceans slightly enriched in the heavier oxygen-18. A spike in oxygen-18 locked in these shells is the chemical fingerprint of a global freeze. Present-day, data analysis. We plot the isotopic ratios on a graph charting the past 65 million years. The data forms a distinct line, tracking the slow, gradual cooling of the Earth. But right at the 34 million year mark, the line jumps dramatically. A sharp positive excursion in benthic oxygen-18 indicates a rapid accumulation of continental ice on Antarctica. The isotopic data demonstrates that the isolation of the continent coincided with a massive temperature crash. Zachos et al. 2001. We can't tell the exact local coastal temperatures of every region from this evidence. What it does support is the rapid global accumulation of ice. The mechanism of the deep freeze is recorded in the chemistry of the shells. It is undeniable. Oligocene, about 30 million years ago, the ice sheets expand aggressively across Antarctica. The forests die out. They are replaced by a barren, blinding expanse of white. This massive accumulation of ice triggers a powerful feedback loop known as the albedo effect. The white ice reflects incoming solar radiation back into space, rather than absorbing it as the dark forests had done. This cools the planet even further, causing the ice to grow larger, which reflects even more heat. Reconstruction shows global sea levels dropping dramatically as immense volumes of water are locked away in the Antarctic glaciers. The warm, flooded hothouse world of the dinosaurs is permanently gone. The Earth has transitioned into an icehouse climate. The oceans cool. The atmosphere dries out. The shifting, freezing winds begin to alter the environments of continents thousands of miles to the north. In Africa, this cooling will fundamentally change the landscape, forcing a small, arboreal ape to face a radically new world. Miocene, about 10 million years ago, the deep freeze echoes across the globe. As the world's oceans cool, evaporation drops. Less evaporation means less rainfall. The unbroken rainforests that once stretched across the equator suffer under a drying climate. In East Africa, humid canopies slowly thin. Reconstruction shows the deep forest giving way to a fragmented landscape. Wide gaps appear between stands of trees. The environment is shifting directly beneath the primates that have lived in the canopy for millions of years. Shrinking forests mean shrinking food sources. Apes are forced toward the margins, where the trees end and the open ground begins. Present-day, geochemistry lab. The technician grinds a hardened lump of ancient African soil into powder. This paleosol is millions of years old. Yet, it holds the chemical memory of the plants that once grew in it. The powder enters an isotope ratio mass spectrometer. This time, we measure carbon. Plants breathe in carbon dioxide, but process it differently based on their environment. Trees and shrubs thrive in wetter conditions. They use a photosynthetic pathway called C3, preferring lighter carbon-12 atoms. Grasses evolved to survive in hot, dry environments using the C4 pathway. They absorb more of the heavier carbon-13 atoms. When these plants die, they leave their specific isotopic signatures permanently locked in the dirt. Present-day, data analysis. We trace the carbon isotopes from African paleosols spanning millions of years. The line on the graph is stark. Around 7 to 8 million years ago, the carbon signature flips. Carbon isotopes in these paleosols show a definitive shift from C3 to C4 vegetation at the Miocene boundary. The chemical record demonstrates that vast African forests died back, replaced by sweeping C4 grass savannas. The dirt proves the trees vanished. Serling et al. 1997, Late Miocene, about 7 million years ago. The environment is a mosaic of woodland patches separated by wide expanses of tall grass. Early hominins find themselves caught in this transition. They are adapted to climbing. Yet, the distances between trees are growing too vast to cross by canopy alone. They must drop to the ground to forage. Reconstruction constrained by limited early hominin fossils, like Ardipithecus, shows apes beginning to navigate open terrain. While models of early bipedalism remain debated, standing on two legs offers distinct advantages in this new habitat. It allows them to see over tall grass. It reduces the body surface area exposed to the punishing midday sun. It frees hands to carry resources. The drying of Africa created severe environmental pressure. Bipedalism provided a biological solution for surviving a fragmented landscape. We can't definitively state that plate tectonics is the sole cause of bipedalism. What this evidence does support is that tectonic cooling created the intense environmental pressure that favored it. The freeze dried the continent. It shrank the forests and forced our ancestors to adapt. Present day, East African Rift, the drone flies high above the Great Rift Valley, capturing deep, jagged scars cutting through the modern landscape. The earth here is pulling apart. Volcanic peaks rise from the cracked crust. Deep alkaline lakes fill the sinking valleys. This is the exact same mantle process that tore Pangea apart. Operating right now. In tens of millions of years, the ocean will breach this valley, splitting Africa in two. We are not the pinnacle of an isolated biological journey. We are a byproduct. We are the downstream result of continental plates colliding and drifting, of deep ocean gateways opening and freezing. The physical architecture of the Earth is a blind, restless engine. It fractured the world, altered the climate, and squeezed life through the narrowest margins. Everything we are today was shaped by the slow, relentless fracturing of the Earth. Late Cretaceous, about 68 million years ago, the world is exceptionally warm. Global temperatures are significantly higher than today. And there are no permanent ice caps at the poles. Because the tectonic plates are actively spreading apart. The new oceanic crust is buoyant and displaced upward, effectively making the ocean basins shallower. The displaced water spills over the edges of the continents. It floods vast tracts of low-lying land. Reconstruction shows North America divided in two by a massive, shallow inland sea stretching from the Gulf of Mexico to the Arctic Ocean. The coastline is dense with lush, tropical vegetation, giant ferns, cycads, and early broadleaf trees dominate the landscape. In this humid, nutrient-rich hothouse, a massive triceratops navigates the dense undergrowth. Its heavy, three-horned skull acting as a plow through the vegetation. The sheer abundance of plant life allows the great herbivorous dinosaurs to reach staggering sizes and incredible diversity. The ecosystem is stable, highly specialized, and deeply entrenched. Late Cretaceous, about 66 million years ago, a piece of rock, roughly 10 kilometers across, slams into the shallow waters off the coast of what is now the Yucatan Peninsula. The impact at Chicxulub releases energy equivalent to billions of atomic bombs detonating simultaneously. The initial blast vaporizes the crust, sending a massive tsunami radiating outward across the Gulf. But the immediate, localized destruction is not what ends the reign of the dinosaurs. Present day, field site, the geologist runs a finger along a distinct, dark line cutting horizontally across the exposed rock face. This thin band of clay separates the older, fossil-rich Cretaceous limestone below from the younger Paleocene rock above. It is the physical boundary of the apocalypse. We test this specific clay layer in labs around the world. It is heavily enriched with iridium. Iridium is extremely rare in the Earth's crust but common in asteroids. This thin line is the fallout debris from Chicxulub settling slowly across the globe. It marks the exact moment the era of the giant reptiles abruptly stopped. Present day, atmospheric context. We analyze the ejecta models and the composition of the vaporized Yucatan rock, which was rich in sulfur and carbonates. The impact launched billions of tons of pulverized rock, soot, and sulfate aerosols high into the stratosphere. Reconstruction constrained by these atmospheric models shows the sky turning a bruised, impenetrable gray. The aerosols act as a global shield. They block out sunlight for months, perhaps years. Photosynthesis across the planet grinds to a halt. The massive, lush forests wither and die. The entire food web, which relied on the constant, immense production of plant matter, collapses from the bottom up. The giant herbivores starve. And soon after, the giant carnivores follow. We can't tell the fate of every individual dinosaur from this evidence. What it does support is an instant global atmospheric collapse that broke the major terrestrial food chains. The blast was the trigger, the starvation was the filter. Paleocene, about 65 million years ago, the dust begins to settle. The world is cold, dark, and mostly empty. The massive, Specialized dinosaurs are entirely gone, unable to adapt to the sudden loss of their food source. But in the leaf litter, eating insects and decaying roots, a different kind of animal has survived the long winter. Reconstruction shows small, shrew-like mammals emerging from their burrows to forage in the ruined landscape. For 150 million years, mammals had been kept small and nocturnal by the predatory dominance of the dinosaurs. But their small size, their ability to burrow, and their unspecialized diets saved them. They required very little food to survive the blackout. They are the ultimate biological generalists. Now, with the apex predators removed, the world is open to them. The mammals begin a rapid evolutionary radiation, expanding to fill the niches left vacant by the dinosaurs. But the continents they are inheriting are still drifting, moving slowly toward new, catastrophic collisions. Eocene, about 50 million years ago, a massive block of continental crust is hurtling across the Tethys Sea. This is the Indian Plate. Millions of years earlier, it broke away from the southern supercontinent of Gondwana, leaving Madagascar and Antarctica behind. Now, it is moving northward toward the underbelly of Asia. Present-day data analysis. We map the trajectory of the Indian Plate using the magnetic signatures locked in its basaltic rock. The data reveals an incredible anomaly. While most tectonic plates drift at a rate of a few centimeters a year, the Indian Plate accelerated to an astonishing speed. It reached up to 20 centimeters per year during its northward migration. One leading model argues this extreme velocity was caused by a powerful mantle plume pushing from below, combined with the intense gravitational pull of a double subduction zone dragging the plate down from the north. This remains debated, but evidence suggests it was the fastest tectonic migration in Earth's history. It was a geological sledgehammer swinging across the equator. Seaton et al. 2012, Eocene, about 50 million years ago. The ocean between India and Asia is finally consumed. The leading edge of the Indian Plate slams into the Eurasian landmass. It is a collision of unimaginable scale. But it happens in absolute geological slow motion. Because both plates are made of thick, buoyant continental crust, neither can easily sink into the denser mantle below. They hit, they compress, and with nowhere else to go, the rock buckles upward. Present-day, Himalayan field site, at an elevation of 20,000 feet. The air is thin and freezing. A geologist examines an outcrop of pale limestone protruding from the snow. Embedded within the rock is the distinct, spiraled shell of an ammonite. This was a marine creature that thrived in shallow, warm seas. We find these marine fossils scattered across the highest peaks of the Himalayas, including Mount Everest. This simple fossil forces a profound realization. The limestone at the roof of the world was once the muddy floor of the Tethys Sea. When India collided with Asia, the immense pressure folded the seabed, pushing it miles into the sky. The Himalayas are not an ancient, permanent fixture of the Earth. They are the crumpled wreckage of a closed ocean. We can't definitively settle the specific mantle mechanisms that caused India's extreme speed. What this evidence does support is that the collision pushed marine rocks to extreme altitude. It reshaped the world. Oligocene, about 30 million years ago, the Himalayas continue to rise, forming an immense physical wall across Central Asia. This wall begins to alter the flow of the atmosphere. Reconstruction shows the high peaks blocking the cold, dry air of the north. Simultaneously, they draw in vast amounts of warm, moisture-laden air from the Indian Ocean to the south. As this humid air hits the mountains, it is forced upward. It cools rapidly. It drops its moisture as torrential rain. The collision of the continents has created the Asian monsoon, an entirely new, massive weather system. The mountains now control the climate for half a hemisphere. But while the northern continents are colliding, the southern continents are finally breaking apart. This triggers an even more severe climate shift at the bottom of the world.